Looks like everybody's coming on back in. We're excited to introduce our last speaker here. I suppose one who really needs no introduction, as you can tell from stories that we've heard throughout the day and stories I've heard yesterday too. A man who's influenced a lot of careers, a lot of which are in this room today. Dr. Hallauer joined the federal and state corn breeding program as a student in 1956, got his master's with Dr. Sprague and a PhD under Dr. Russell. And from 1963 to 2003, he was an employee here in ARS and with the state program, was involved in the release of the B code lines B37 through B121, some of which are still prominent in our pedigrees today. Their success led to our current classification of heterotic groups, the Iowa stiff stalk synthetic types, and the non-Iowa stiff stalk synthetics, training many successful graduate students, some of which I see in the room today, and continues to share his knowledge with us over a few bags of popcorn every morning. Dr. Hallauer is recognized for his dedication and efforts, being elected as a member of the National Academy of Sciences in 1988. If you join me in welcoming Dr. Hallauer.
Thank you, Gerald. At last, we got a crop that originated in the Western Hemisphere and cross-pollinated. So after a long day, we'll switch gears, and it'll be an entirely different type of crop that we're working with. Buttons push up. Does that work? Okay. Here's a brief outline of what I'll be bringing into discussion today. Of course, origin, where and when are the punitive, or what are the punitive parents of corn? I'll use maize and corn kind of crossways here because maize is a more popular word internationally, whereas we're more familiar with the term corn. What is the origin of the U.S. germplasm, which involves the northern flints and the southern dents? Then eventually we have then what we call the most productive race of corn in the world, the old U.S. Corn Belt Dents, primarily represented by the open pollinated varieties that we had. And then those were the original breeding materials that we had in the programs in the U.S. There was concern that yields were not improving, so there was looking at alternative methods to improve corn. So the hybrid corn came in, and this was primarily suggested by a series of 3 papers by George Harrison Soule in 1908, 1909, 1910. And if you haven't read those, particularly the 1910 publication, he explicitly outlines how, develop lines, test them, pick the best one, produce it, and distribute it to the farmers. Those single crosses. The current germplasm we have, and pedigree selection is so important. Well, it's primarily the only thing it's probably used in the majority of corn breeding programs. We have synthetic varieties available in exotic sources, but in so many instances they don't quite meet the standards that we have crossing good by good in F2 pedigrees. And what are the outlook? Taxonomy. Corn is in the grass family. So hello, crabgrass. Tribe Medii, Zea, genus. Now under Zea, we've got the species, of course, Zea maize, corn. There are more than these few Teosinte species I've listed here, but Teosinte, as I'll show a little bit, is pretty much assumed to be the parent of corn. There's a lot of research and debate in the first half of the 20th century about what the punitive parents were, but it's pretty well resolved now. Then we have Tripsicum or gamma grass. Now Teosinte, the people that really work with it can make the crosses and get fertile progeny out of it. Now with Tripsicum it's been more difficult, but if you look at the chromosome number you can see why, with 2n equals 36. And there's several, 13 to 15 different species of Tripsicum. Of these Teosintes, Zea diploperennis is the newest one. It was about in the mid-1980s when a Mexican botanist by the name of Guzman Iltis from out of the University of Wisconsin found Diploperennis in the hills east of Guadalajara. And there was some interest in it at the time. Walt Geppinger, a farmer over here by Boone, Iowa, about 16 miles west of here, became an activist. He was very active in developing the State Corn Growers Association, National Corn Growers Association, and so forth. And he grabbed hold of some of this Diploperennis and brought it up here and was growing it over here east of Boone. And I took some students over there after pollinating one day, and it did look. He had a group of clones from here to the wall. It looked quite nice. It made the front page of the Des Moines Register. He gave a presentation over at the Iowa Academy of Science at Cole College in Cedar Rapids, and boy, it looked like, you know, we could grow corn like we could grow grass. Well, after next spring, though, we never heard anything about it. It didn't tolerate freezers or cold temperatures. So we've never heard anything more about Diploperennis, except, by gosh, I got a Maize Co-op newsletter yesterday, and there's still a guy working with it where he crossed it to B73 and was describing the different things that are coming out of it. So it's not lost yet. There's what teosinte looks like. No, that's not switchgrass. That's a presumed puniferent of corn. It grows in the wild, which is why one of the precursors for a decimated crop was it could survive in the wild. And now this particular was grown down in Mexico and in places, and still if you drive over from Mexico City to Tautizapan, why, you can still see teosinte in the ditches and along the inrows and even within the cornfields. So it's able to survive. It can cross with corn, and it has a lot of the traits that are necessary to have as a wild relative. And there's a kernel. If you compare the kernels, present-day corn with large kernels on a cob, all tightly packed together, and it drops on the ground, why it's such competition among them, it can't survive. It requires human care to survive today. And there's the teosinte kernels on the 2 rows, horniest texture on it. They could survive and get scattered about in the ground, which is why it was a wild weedy species. There were a lot of hypotheses, punitive parents of corn, until about 1980. Different people such as Paul Mangelsdorf, Gallinat, Garrison Wilkes, and those had different theories about it. And the conclusion was, based primarily on the molecular work that Dobley did at the University of Wisconsin, that teosinte is. Now, George Beadle in 1865, about that time, gave a presentation at the American Seed Trade Association meetings in Chicago. And he was rather certain at that time teosinte was a parent of corn. Now, whether it's intuition or whether he had experimental evidence, I don't know. Some still disputed it until Dobley, with the work with molecular biology, looked at chromosome configurations and so forth, concluded that was indeed teosinte. And then even Paul Mangelsdorf, who had been several different theories, he agreed that indeed teosinte looked like to be the punitive parent. He had the tripartite theory. Edgar Anderson was there at Botanical Gardens, said somebody, possibly even the Asian species, as Coix, Polytechus, sclerochia, and some of those might be. But present day, it seems pretty well established among most people that teosinte works. Now, in the Western Hemisphere, it originated in southern Mexico, northern Guatemala, and that rough area down in there. And there's a lot of valleys and places where different communities could work. 10,000 years ago, approximately, and that seems to fit in with most. When you look at the old literature, that 10,000 year mark always comes. Even in a recent issue of National Geographic, the garden pea that old Gregor Mendel worked with was domesticated 8,000 years ago. So corn fits in that same category as the others. And within the Western Hemisphere, there's been 285 races described. Goodman Brown, 10 in the U.S. And the migration of the natives north to south had a lot to do with the movement of corn in the Western Hemisphere, all the way from southern Argentina up into the Great Lakes area, southern Canada, and northeastern United States. By the time then Columbus arrived in the Western Hemisphere, why, the natives had corn. He carried some back to Europe. And within one generation, corn had spread throughout Europe. Within two, the world. Now, Paul Manglesdorff, in his book, he made a comment that corn was the third fastest organism to be distributed around the world. And number 1 and 2 were wheat, rice, no, syphilis and tobacco. So we're in a very good company there in our distribution after the Europeans discovered it. In North America, when the Pilgrims arrived in the Northeast, why, corn was also present then. And then in the southern part of what we now know of the North American continent, why, we've heard of Ponce de Leon, but there was an old guy by the name of De Soto. He trudged all the way from northern Florida, across Georgia, Alabama, Mississippi. And in all instances, he found that the natives were growing corn at that time. So we had corn pretty much distributed already from the Florida to the northeast of what present-day United States, up around the Great Lakes of southern Canada. Now, the northern flints. Well, the proposed origin of that is from the central Mexico plateau to the southwestern part of the U.S. Now, this has been pretty well established, too, that Chapalote with a 12-row popcorn was crossed with a Unoso de Ocho, an 8-row, and this cross led into the Pima Papagos and eventually the Maize de Ocho. So that was the source of the northern flints, and that was in the southwestern part of the United States. Now, how in the heck did it get up in the northeast when the Pilgrims arrived? Well, there's still some question of how that has happened, but I assume that, that the movement of the natives from across the prairies and along the river valleys and perpetuated corn until they eventually got up in the northeast, and they had to have early corns in order to survive those type of environments. So the movement from the southwestern part, what was present-day United, up to the northeast, is kind of problematical, but they think it's happened that it could have been just movement of the people. And then when you read about old Chief Blackhawk running all the way from Davenport to Detroit to get more ammo to fight Jefferson Davis and them, well, I expect he could have carried some corn too. Traits, early maturity, short, flinty kernels, flag leaves, tillers, 8 rows primarily. And it had a small tassel. So those are some of the traits of what we designate as the northern flints. Southern dents. Here the evidence seemed more clear. That was the Tuxpanio race from the coastal areas of eastern Mexico over to Cuba and eventually over across, that's not very far from Cuba, to the Florida, and then moved and distributed in the southeastern part of the United States. The punitive parent of Tuxpanio, they have been traced to the cross between Olatia and Tepeceno, and contrary to the northern flints, it had a very different phenotype, of course, a long growing season. It was tall, late maturity, large tassels, 30 tassel branches or more, limited or no tillers, more kernel rows, and soft dent rather than a flint, 8-row flint. It was a soft dent with more rows. And of course, back, around the Civil War time, the Corn Belt in the U.S. is in Tennessee. Soft dent producing alcohol, right? Only they called it moonshine. So the U.S. Corn Belt dents then, it was then from the northern flint to the southern dent. And as the eastern seaboard was colonized and people moved north from the south and up north, down south, why, of course, they carried corn. And when you had wars or armies, why, you had horses, people you had to feed, and so corn was carried about also. So you always had to have some feed for both the soldiers and the horses. So there's either accidental or planned crosses when you had this commingling of the northern flints and the southern dents. It was out of this commingling of them, up in Northern Virginia, Maryland, and that general area, southern Pennsylvania. Why then, accidental or planned again, you had accidental crosses between them, or maybe some individuals planned to make the crosses between, probably more accidental than planned. So out of this cross then, between the northern flint and the southern dent, we had what then we call the open pollinated varieties. And like Lemming, there's some question of how early he did this, but Jake Lemming, he was developing the corn along the Ohio River Valley north of Cincinnati, up in that area. And he was looking for an earlier corn that grow in the deep loamy soils along the rivers. He had a tapered ear, and he really had a precise way to estimate maturity. Whichever ears the crows are feeding on the tip, he put a red tag on it. And when he went back at harvest, then he harvested those ears for a measure of maturity. Reed yellow dent, this is probably one in the corn breeding lore more than any other open pollinated variety. Robert and James Reed, developed this variety over in the western part of Illinois. And again, it was kind of an accidental cross originally. He brought with him when he immigrated from Ohio, Gordon Hopkins corn. And apparently in that new area, and then that wet spring, it didn't germinate too well. So then he had a secured seed of little yellow and plugged in between. Well, from that cross of Gordon Hopkins, a little yellow, arose a Reed yellow dent. And again, that had more fame probably than any other open pollinated variety. It won the World's Fair in Chicago in 1893 and sold as much as $50 a bushel. So, that was a lot of money in those days. Lancaster sharecrop, this is Isaac Hershey, and he developed that again by introducing corn from both the flinty and the dent types, and he had kind of an open-ended population. And he occasionally entered corn that he thought would better. He selected more a cylindrical ear, smooth the kernel than what the Reeds did. Then Krug, he took Reed yellow dent. At that time, he didn't believe in how pretty it looked. They had the scorecards back in those days. And he selected more for a rough type, more what he thought was high yielding. He was a farmer over in Illinois. Krug, you don't hear too much about. There was one line that came out at 187-2, and it was involved in some early lines. Particularly, it was crossed with C103 to form a 017. Iodent, that was here in Iowa. L.C. Burnett, he was a small grain breeder here in the Department of Agronomy. He did one of the first ear-to-row studies I know with very intensive selection, and he ended up at 2 ears. And he crossed those 2 ears in and formed what we now call as iodent. Now, iodent, you hear that still a lot in the corn breeding notes around. It was a variety that was grown in northern Iowa, a yield test. It's kind of an early variety. To me, it's not that early, but at that time, they grew it in kind of north central Iowa. It never won, but it's always in the top 05. Midland, that was a farmer named Rhodes down in southeast Kansas, developed that. There's been some lines out of it. Midland's been a source of some lines that had corn boll resistance and drought tolerance. When I grow it in Ames, though, it's like introducing a tropical variety. It's late and tall. Minnesota 13 up north, that was another one that's prominent in the literature. And they think probably the north was involved with that and perhaps some cross with later materials to get yield. So those are just some that they all used more or less phenotypic mass selection. There was no yield trials, no standards out there in which to base their selection on what their own visual had in mind. And Sturdivant at Cornell at that time, at 1899, there's probably 100 different open pollinated varieties. Well, you see here, there's some that's developed like Krug and Iodent and Midland and some of those after that time, so that there's probably 250 open pollinated varieties. How did it develop? It was all individual ears. There was no male control. Cross-pollinated, and pollen was flying all over the field, and they were basing their selection only on the female. There's no environmental control. That is, it wasn't replicated. Gardner in recent years had the grid system of mass selection. That was not used. If you had a field that had, some elevation on one side and fertile soil, more fertile soils at the bottom, more moisture, well, maybe the greater proportion of ears were selected on the lower part rather than on the upper side because it just didn't get the amount of nutrients or moisture that was down there. Then maybe just as high yielding. But they selected them. So then came along the corn shows. In the mid-1880s, there's a guy named Furman over in Illinois. Got together 18 guys. We need to improve yield of corn. How are we going to do it? We're going to design it. So those 18 guys sat around the whole day and debated on what traits they should use. And it all was based on traits. None of these guys were individual farmers. None of them, well, they farmed, but they were not breeders or selection, hadn't developed a Reed, hadn't developed a Krug or anything like that. But they made up their minds how they could visually perceive what should be high-yielding corn. So the scorecard was developed. And, of course, eventually, questions were asked. Like Henry Wallace here in the early years of the 20th century was wondering about, again, when he observed what they had the corn shows over in the old armory, did that pretty one that looked like win the prize? Would that also win the prize for the highest yield? But again, the winners depended on the patience and time they took to select their ears. If you had a 10-ear sample, well, how much time, to get to compare each and every ear that you'd harvest to get a uniform sample of 10 ears that appeared to the judges to be conform to type. So it's all done by mass selection and is phenotypic. Now here's an example. This comes out of a book published in 1908, General Appearance, just looks, 20 points, that's 1/5 of them already. Trueness to type, 20. Just the shape of the kernels, straight rows. How straight were the rows? If that made any difference for what yield, but how straight. Maturity, just looking at the ear, the size of the ear, plumpness, moisture. They didn't run moisture samples or anything. Vitality, looking at the cob, the size of the germ, condition of the cob, there's another 25 points. Shelling percentage, the depth of the kernel primarily was determined that. So he ended up there, that the a scorecard that was describing what an ear should look like just on phenotype. It was like showing a steer at the county fair or something, you parade it around, looks how pretty, and it appears to the judge, and he says that's number one. Now, maybe it doesn't have the best ribeyes, but it looks good. That particular one there was by Bowman and Crosley. So what did all this work have where we developed open pollinated varieties of corn that occurred during the early part of the 1800s to 1850 and continued on with the scorecards in the late 1800s, early probably 1910, 1920. And then what impact did that have on yield? Well, here I show the average yield of corn for the United States from 1865 to 1935, 70 years. And you see there's not much of a trend there anywhere because there's only 4 years among that 70 years that yields exceeded 30 bushels an acre. Only 4. I had those here in 1896, 30 bushels. 1905, 30.9. Now we're on a trend here. 1906, 31.7. 1920, 30.3. And even then in 1941, it's still only 31.1. So you can see all that work that went into that had not improved yields of corn. If you really want a good one, 1936, 16.2. That's when the first global warming went through here. But also in 1936, there was a little bit of hybrid corn out there, and it did better than the open pollinated. So that was when really the hybrid corn got its start, or at least is noticed by the producers and farmers because it had done better than the open pollinated varieties. Now, I take here as just one example where they were selecting. During the late 40s and during the 50s, there was work in quantitative genetics. Quantitative genetics back in those days was like molecular genetics. Today it was a kind of the glamour boy of research. And there's evidence that ear length was associated with yield positively. So you had a positive correlation. So why not just select for ear length? Well, in 1963 I got 27 years data here, but I did it for 30 years. Then I evaluated it, and you can see I was effective. I got longer ears and shorter ears, starting out with the same base. First year is in the same population, field. After that, separate isolations and selection from one for longer, the other for shorter. And it was very effective. What did it do for yield? Well, you can see right here, not much. There's a little bit of a negative one even in the long ear selection. And then, of course, the short ear. So that just selection on, you know, one or two phenotypic traits did not have an effect on yield positively. Now, this is not only done for ear length, but other people have done it for shelling percentage, kernel depth, number of ears, and other ear traits. It has never worked. So here, you know, it's been very effective developing two strains of corn, but it did not work as far as trying to improve yield. And then there's a correlated effects. Look at just the difference in plant height. You know, the long ear, it had the long ears, it's taller, later, tend to lodge more. The shorter ears had a shorter plant stature. So that not only did it affect the ear size, and indirectly it affected yield and other plant and ear traits. Baumann in 1981, he also surveyed the corn breeders in the Corn Belt. And he asked them a couple of questions, the importance of traits for, I listed here, 9 of them, different traits, how important they were, and how effective was visual selection. That is, looking at it rather than having yield trials or some other type of trials. And 1 is the best, so if there's a 1, you know, well, like yield, 1.2. That was a very important trait. Well, then if you look over there, how effective is mass selection? 3.2, pretty poor. Or if you look at flowering time, that's important for relative measured maturity, and 1.3 relative effective. But as it overall, though, it ended up a negative 0.76 between what we do visually and what the importance of the trait. The importance of hybridization has always been significant in corn breeding. Even before we got to hybrid corn, it's cross-pollinated. So in the development of these different things I just list here, you know, the northern flints I mentioned, the Chapeloti by Hernosa de Ocho, southern Dents, the Tuxpeño Otillo by Tepocinto, Reed Yellow Dent, Gordon Hopkins, a little yellow. Reed's yellow is Iodent, but late yellow dent. McCullough's, probably the north, but Reed yellow dent. Iodent, cross between two ears, and so forth. So even our open pollinated varieties during this period of time, a lot of those have been developed by making crosses between other cultivars and then selecting within those, such as Reed yellow dent and so's. Early studies. All this is done, as I showed you on there a couple of slides ago, nothing was done about yield. There had been suggestion of variety crosses by Beal in Michigan in 1880. He had shown that there was an advantage to crossing varieties, but there wasn't such things as the 3 R's of randomization, replication, and repetition to separate out and find out what the experimental area is. So that Ritchie, he summarized about 244 different instances where open pollinated variety crosses were compared with the parents of the two cross. And then he looked at the mid-parent and high-parent response into the variety cross. And he decided about like flipping a coin where they were better or worse than one of the parents. So it never caught on, but again, the experimental procedures and methods were so poor back in those days to measure the differences of, besides just observation was probably not too good to really detect if there's real differences there or not. So there was a vast expansion of people from the East Coast moving west, Ohio, Indiana, Illinois, Iowa, Nebraska. And they had a lot of livestock with them. They had hogs and cattle and chickens. They had to feed them. And here, the 30 bushel corn wasn't really meeting their standards of the amount of feed they needed and so forth. So there's always the urge, more, greater yields. They tried scorecards. That didn't work. They tried variety crosses. That didn't work. So then, with the rediscovery of Mendelism in 1900, well, then, of course, corn became a pretty favorite organism to work with because the male is the tassel and the female the ear. They're easy to manipulate between crossing and selfing, and you get a lot of seed. So there's a lot of interest in corn, and they did a lot of genetic studies. Darwin had done some earlier too, but then Scholl came along. Kimmel, Collins did inbreeding. I should have mentioned East there, I didn't include him. All those, were looking at corn and noticed that there's a drop-off when they selfed it. There's a little jump when they made crosses. But it was Scholl again who really laid out the foundation for it. And again, the source population in Scholl's study and subsequent studies was always the open pollinated varieties. And, it was a source of germplasm. And here's just an example. So Scholl laid it out in 1910 very explicitly. If you read his 1910 paper delivered at a breeders' conference out in Omaha, Nebraska, he called it the pure line method, get inbred lines, cross them, test them, find the best one, give it to the producers then. Well, you know how new technology, that'll never work. Well, at that time it didn't work so well because the inbreds were rather weak, poor. We didn't have any Roundup in those days to kill the weeds, and the weeds pretty much swallowed up the inbred lines, and they had low yields to begin with. So, most people just didn't consider it very practical. Then Jones in 1918, 1919 said, hey, why don't we cross two single crosses? That is, produce single cross 1, single cross 2, and then cross the two crosses together and get a double cross. Oh, that might work. So there was again a big push, greater yields. Henry Wallace, not Henry A., his dad was in the Secretary of Agriculture. They, I'm sure, had an important, significant impact. We're going to try this new method of Scholl, of combination of Scholl's ideas and Jones' ideas, and see if we can improve yield that way. A different approach than what we've been using with scorecards and varieties. Well, then that got underway, and so a major effort was like, the Sputnik thing, flying over here in 1958, beep, 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 beep. Well, we had to have mathematics, we had to have physics, we had to do this, catch up with the Russians to get a Sputnik running around up there. Well, we had a major effort started in 1922. F.D. Ritchie from the USDA was in charge of it. And about every experiment station in the country started a corn breeding program, as well as the USDA throughout locations in the U.S. Well, here in Ames, Merle T. Jenkins was in charge of it. First nursery had 469 rows. His source populations, you recognize them all there. They're open pollinated varieties. They were done well at the state corn yield test. And so then we went to work then following this concept of Scholl and then the double crosses, and the rest has been more or less history. Well, you saw there then that from 1922 to 1940 yet, corn yields were not too good. Most of the time, all of them were less than 30 bushel an acre. Why the delay? Well, everybody went out and selfed and got inbred lines. The trouble was, which one was the best in hybrids? They might look pretty, have good roots, maturity, but do they make a cross? So how best to identify the best lines, and that was much more difficult than developing inbred lines. Well, even, even if you got 10 lines, 45 single crosses or 630 double crosses. Or if you got heterotic groups, I'll get to a little bit, while you can have 25 single crosses. Same way, what if you got N equals 50 inbred lines, which wouldn't be unusual for anybody in a selfing nursery to have 50 lines he needs to evaluate. Well, that's 1,225 single crosses, 700,000 double crosses. How in the world are we going to do this? And so the concepts of test crossing, getting data from test cross, single cross data, predicting double crosses, and then testing double crosses. So there's a lot of lag time in there, time you make all those crosses and evaluate them. And experimental techniques came in, in 1927 when Fisher said you needed replication, randomization, repetition, and so forth. So there's a lag time there, but really it was getting the techniques down to evaluate lines. And there was poor relationship, again, like I showed you earlier about the ratings and physical traits and how effective visual selection was. Same way, there wasn't any relationship between inbred lines and hybrids. The test crosses, of course, every corn breeding conference you went to in the 50s, 60s, early and late. Do you test early, test late? S1 sage, S2 sage, or S6 sage, or S7 sage. They didn't get in fist fights, but pretty close. I'm for early testing, you're for late testing. But Bernardo, he finally figured out early testing, then predicted color. Then we come to the heterotic groups. What are they? How did they develop? Well, they're not something that occurred naturally anywhere. It's something that was empirically determined by the corn breeders. And, of course, then heterotic groups, what is the basis of heterosis? Well, Falconer has this elegant little formula, a very simplified version, that the genetic base is the summation y squared d. That is, you had to have, if d was 0, there would be no heterosis. If d is not 0, the magnitude of heterosis depends on y squared, which is p minus q squared. So the greater the difference in gene frequency then, times d, which is not 0, the greater the heterosis. So then we wanted to look at heterotic groups to try to pull them apart to get the greater amount of difference in gene frequency. Well, in 1949, we had a heterosis conference here, and dominance was a thing. Overdominance and dominance. In 1999, the conference was repeated in Mexico City. It was dominance and epistasis. So everything was non-additivity in both cases, so that, 2 plus 2 equals 4, but 2 plus 2 equals 7. What's going on here? We got the interactions to account for. Now, how they developed, again, was empirically, and this came through by 1940. They were looking at the different hybrids, the pedigrees of different hybrids. Look at US 13. That there was a reed yellow dent, high yield, Illinois high yield, which it's not clear. They think there's some lemming germplasm in it, and L317, one of Jenkins' Lancaster lines. Iowa 939, Sprague told me that was the greatest, widely grown double cross ever, and that was confirmed when I read the book by Hybrid Corn Makers by Crabb. And look at the pedigree of that, OS 420, OS 42. That is Australian, which developed about 60 miles up the road here, crossed with Lancaster 289, I205. Now Lancaster again, but then I205, the iodent. And there again, you see, you had the reed on one side and something non-reed on the other side. You take Iowa 13, it never did as well because you had Lancaster by reed and reed by reed. So you had 3 reed lines in it. Well, in short, come down here, Eckhart and Bryan in 1940, then they reported data in American Style Agronomy. Hey, you want A by A as one single cross and B by B, and it was higher yielding, more uniform, and so forth than if you had reed by Lancaster, reed by Lancaster. So that would pretty much put them in place, and in the North Central corn breeders, they developed heterotic groups by grouping the inbred lines for breeding purposes. That is, if you want to cross good by good, make the good inbred and reed by reed, and then the good in a Lancaster Surecrop group. So don't cross between reed and lat. Cross your best within the heterotic groups, and then test them against the other one. Some crops, have had heterotic groups. Of course, the reed yellow dent and Lancaster. Now you talk about Iowa stiff stock, synthetic, and non-stiff stock. Europe, U.S. Dents by European flints. Argentina, U.S. Dents by Argentine flint. Tropical areas, Tuxpanio by Edo, that's kind of out of fashion now. Tuxpanio by Su11. There's other ones suggested. The DeKalb people, Kaufman and them, said that lemming by Midland may be a potential, another heterotic group in the Corn Belt. Of course, a long way to go to catch up with the others. So there's what happens. You got the reed on one side, Lancaster on the other side. Look at the traits, how they complement one another, and then you get the F1 cross. They seem to be double crosses were plateauing by the latter part of the 1950s, early 60s. Then they're beginning to question themselves. They keep sampling the open pollinated varieties. They weren't doing any better. And if the sampling had been adequate, there's a reason to expect why it wouldn't be any different than what they had done 30, 40 years earlier. And then in 1961, Cockerham, in the very first issue of Crop Science, published a paper in which, even if you have non-additive genetic effects, the efficiency of selecting among single crosses twice what you would among double crosses, with 3 ways intermediate. If you've got serious dominance and epistatic effects, the advantage is even greater to select among single crosses than double crosses. And Cockerham, he was a student here in J.L. Lush. He probably never been in a cornfield, never made a self-pollination, but he sure did a lot of good for corn breeders in that theoretical paper of selection, because we were beginning to question what we were doing at that time anyway and how we should change things. So it came in about that, we had to switch from doubles to singles in order to continue that trend in yield. And so then, how do we improve our germplasm? And things came about then. There was a great debate again at that time, the importance of additive effects, the importance of dominance and overdominance and so forth. So different selection materials or procedures were suggested to improve our germplasm from which we could extract lines. There's limiting factors in germplasm versus the pedigree of good by good, of course. There's always the difficulty on the different traits to meet the standards that are needed in modern day hybrids. Exotic, what I could include is what's not really immediately available to breeding programs. Midland from southeast Kansas is as exotic to me as, say, Tuxpanio from Mexico. So all those require adaptation. Look at our germplasm, an example. I got to hurry up here. Iowa stiff stalk synthetic, you probably all heard about it. George Sprague, he initiated by crossing 16 inbred lines in 1932 at the Arlington Farms. If you're in Washington, D.C., look over there and see the Pentagon. That's where the Arlington Farms was in those days. It's mostly reed. He brought it to Iowa when he transferred here and initiated selection programs in 1939, 1949. And Jody Edwards, I think, is still continuing those today. But the important thing was integrated basic and applied information. We wanted to try and test the different methods of selection, whether they emphasize additive effects, or whether they emphasize dominance, or emphasize additive endominance, or epistasis, or anything. If we do all that work and we show gains and get a nice glossy paper to get promotion and tenure, does it contribute anything to corn breeding? So in order to give relevance to what we were doing, we weren't trying to compete with any companies, because I was told in 1958 you aren't supposed to anyway. But, in order to give credibility to what we're doing, we always piggybacked or, snuck in test cross and single cross trials. And that was only about 10 or 15. If I had 30,000 yield test plots, only 3,000 to 4,500 of them were involved in single crosses and test crosses. But we continued our, our theoretical basic studies. And out of that, see, just piggybacking out of here, out of our 10% effort, these lines were released. There's from 1953 to 204, just out of stiff stock. Now, some of those, you recognize had quite an impact, others didn't. You notice back in the days, very modern, homozygous diploids, B67, B69, were developed out of stiff stock synthetic with SS Chase at his purple cell marker that had haploids too. So how much they've ever been used, I have no idea. So not only were they used for, directly to produce hybrids, but they could also be parents in recycled lines. So this is from MBS. Here they listed B14. There's 112 different versions of B14 floating around out there. 57 versions of B57. Now there's fewer of those than B14 because they could never get an early version of B37. Like B14 moved up to Minnesota, the A lines, up in Canadian Morden, the 105, but they couldn't get a B37. And then, of course, B73, and we got B84, 161. This is in 2000, and probably 161 more of those. Why BSS? Well, one thing is put together with reed yellow dent germplasm. Another thing, all the lines selected into it were there because of above average stock quality. So we had those two things, but also I did a lot of genetic studies with it. And I got here stiff stalk compared with corn. There's over 5,000, 6,000 plots of data in that stiff stock up here. Gerald told me he didn't want any sigmas in this symposium, so I took out the sigma and put V. So this is the variance due to additive effects, variance due to dominance effects, and the ratio of them. You can see it's about equal for stiff stock. Now, like I say, that's not a random number. There's about 5,000 to 6,000 plots of data in there. Now in corn, this is 99 different studies I've researched. I tried to find 100. I couldn't get that 100th one. But you see there, the additive genetic variance is much larger than the dominance. So how much the genetic composition of it may have had on the success of stiff stock synthetic, I don't know. Tropical, they say we ignore 98% of the germplasm in maize. We're only working with a base of less than 2% of the total germplasm available. So there's all that tropical and semi-tropical out there, but it's difficult to work with because it's photoperiod sensitive, not adapted to here. It doesn't meet the standards that we have. But there's a lot of, we looked at, if I grow one of those populations out in my nursery, that's what it looks like. See, it doesn't flower until the latter part of August. There's old Paul holding the graduate student trying to get up there to the ears. Just using mass selection, I had large population sizes, about 10,000 plants, and select 500, 300 to 500. And I did that, you know, for 5 to 8 years in these different populations. You can see in the bottom line there that it's about 3 days earlier on the average every time you do it. So if you do it 6 years, you got 2.5 week earlier corn. And that's what worked out for me. And you brought all those in, and they're now adapted. And then the two of them, Tuxpanio and Su-11, well, I had 5 cycles of reciprocal half-sib selection completed in them. And when they're out in the yield test field, they're just looking like normal corn belt corn. Now, those populations were not selected at random. Edel, I run down to Des Moines with Bill Brown. He suggested that one because it's very important in the tropics. Antigua had a lot of disease resistance they found. Of course, Tuxpanio was one of the major ones in the tropics, and Su-11 over in Southeast Asia. So I just didn't randomly choose corn to work with. I'm getting down to the end here. Here I summarized all the selection studies we've done from 1939 to 2002. It's a kind of a busy slide here, but it shows what happened with intra-population, and then inter, where there's 2 populations involved. There's 8 different studies here, and there's 7, 13, 14 there. And then down here, Roger Warwick, he did a series of studies with NBS 11. But the punchline is down at the bottom here, it's about 4.3 over all those studies, about 4.3 bushels per cycle gain. That doesn't seem like much, but it's you do it enough times, 20 cycles, you know, you got what? A lot of corn. What we did versus pedigree. Now, there will probably never be this repeated anywhere, but Don Duvick did this. He looked at the recurrent selections being done at Iowa. He looked at 2 experiments he was conducting at Pioneer with pedigree selection. And you notice there at the end, it comes out there very similar rates of gain per year of the pedigree versus, now for emphasis, he used 3 years and 13 years. Even when I go back and took 2 years and 8 years, 1.8. It's very similar what we were doing, what he was doing. Of course, I told him if you use the lines that came out of it, they should be. Improvement, is it genetic? There's been tremendous improvement made in agronomic, handle people, husbandry, how people handle their fields, combine in a more timely manner, better planters, GPS, all that. And I've only listed here, 1, 2, 3, 4, 5 possibilities here of comparing hybrids from different eras. And in short story is, and I say there's a lot more of those, it's about 60% or more than 50% of the gain in hybrid yields was due to genetic gain, and the other 50% due to improvement in management and husbandry practices and so forth. So the corn breeders have been, here Beatty did a similar study in Argentina and found the same results. I forget the name of the guy in Serbia. at the breeding station there, he found the same results. So it's fairly consistent, at least 50% of the improvement in yield is due to genetics. If we look at this, you see with the later years, a little bit surprising here that some of that, it kind of tapered off a little bit. Troyer also has it up to 2013. I haven't got mine updated yet. But, there's in here single crosses, and in here the later years, our biotech hadn't taken off yet. I've done a lot of, I looked at 2001 to 2010, and the rate of gain there is about 2.47 with a higher error, though, of 1.4. Now they say we're going to get 300 bushels per acre by 2030. Well, we got to double that rate of gain if we're going to make it. I don't know. With more restraints you get on people that don't farm, I don't know whether that's going to be achievable or not. Acreage, you look at it, in 1932, that was the year I was born. Look at that. 110 million acres of corn. Wouldn't those companies like that today? Yield, 24.6. Price, 36 cents. Looking down at 2012, we got 94 million acres and 12 billion. That's, this year around 14 billion on about that much acreage. Yields were a little lower then, but then the price was 586. So you can see there's been a large 6 times increase in yield, at least 8 times, pretty close, at fewer acres, and total production is up. So the methods that the guys have been using has certainly gone up. Continued, recycle, recycle, recycle. That's what we need to do for continued, and that's what the breeders do today. Good but good within the heterotic groups. It's a proven method. There's been persistent genetic variation. They say we're hitting bottlenecks, but it seems like we keep moving along. Recurrent selection is for genetically broad-based populations. That's not an acceptable method for commercial breeders because of the competition. I think it has to be done probably in the public sector. It is effective. It provides a source of unique lines. It's not recovered B14 or BA73 or something. We hopefully come up with something new. But in order to identify those lines, you have to integrate your basic research with your applied research. And you don't have to, as we found out, you don't have to make a major commitment to it. 99.9% are in the garbage, but you're always looking for that one unique line, whether it's a B73 or something like that. Also in the future, this would be worth looking into as a whole new program, is LAMP. And here's the recycling I've showed here, how it's going around the cycle here in the U.S. They had the lines that form stiff stock, and they got these in major, the major importance. Populations work. On my full SIB program I started in 63, I have same 6 hybrids. 3 singles, 3 double crosses, every trial since 1963. And that's there. The reason I got 3 singles, we're just switching for doubles to single crosses. Original, I started in 63. I got over here. There's only 4 of the full SIBs that were greater than the mean of the Czech hybrids. Time I did 7 cycles, the mean of the crosses were on the Czech hybrids. Now the last one I conducted, you can see it's completely transposed the population from below the mean of the Czechs to over the mean of the Czechs. And that was one of those in that summary. So if you do it enough, and that's the whole goal, is keep recycling, recycling, recycling. Of course, if your heritability is perfect, it'll be setting, the new population be sitting right on top of it, but it's not. But you just keep going and incrementally increase gene frequencies. And I think it's the same way in pedigree selection with crossing good by good. You try to make incremental improvements in gene frequencies, increase the frequency of the favorable alleles from cycle to cycle. And it never ends. It's always going on. And what we're doing as breeders, we're always crossing, regenerate, get recombination, genetic variability, select. Lamp and Jim, that'll be the hope in corn for the future. The university programs are pretty much dwindled out. People retire, die, or go with a new person who doesn't want to mimic or copy what the previous person did, or there's been a change in goals. So that germplasm is on the downslide and has been for several years. But the LAMP program, then this got started again with Bill Brown. He moved up to president of Pioneer at the time, and he had always spent his career in germplasm and South American germplasm, Caribbean and so forth. So this was administered by the USDA and the evaluating sessions. Now they did this because they were losing their germplasm. People were not maintaining their facilities, didn't have funds. The humidities were high, we're losing germination of the seed. So they grew 12,000 of them. It was a rescue operation. They did have 2,000 and they selected and evaluated. And then each country then was going to improve those that were selected. But again, funds were lacking, personnel were lacking, interest was lacking, it wasn't getting done. But within the U.S. then we got the GEM program. Like I say, that's a consortium of both the public and private breeders. And that would be worth a seminar itself to do what they're doing. Summary, we originated in the Western Hemisphere. It's pretty much like the other crops, 10,000 years ago. Pretty well established. Teosinte was the parent of corn. The U.S. germplasm that arose out, that's pretty well documented as the source of between the northern flits and the southern dents. The corn belt dents then were derived from that cross between the dents and flints. We had a lot of open pollinated varieties. They were the original germplasm sources and breeding programs. They've been pretty much replaced this year. And then in hybrid corn, well, they had a series of people that were involved there that made sure that we... So the current germplasm, it's pretty much good crosses for the commercial breeders. It's competitive industry out there, so they got to use as lead germplasm they can in order to be competitive with their people. Recurrent selection can improve programs. It's long term, but it can work. It's been demonstrated. You can fling off a lion here and there that can be of some importance in the seed industry. And of course, that 98% germplasm out there is a lot of work to adapt it and get it improved to where it is. So future germplasm, continue to recycle what we have. There's, of course, GEM that can carry us. And, of course, the whole thing of molecular biology for specific traits. And I'm sure if we're going to get 300 bushel corn, they're going to have a big impact on that in the next 15 years. I'll quit there, Gerald. I went overboard. Yeah. I can get out of questions now.
Thank you very much, Dr. Hallauer. We'll take 2 questions, so then we can keep the program moving, but we do have time for a few questions, so.
They're tired. Oh.
Since nobody else is going to ask a question, when George Sprague moved to Illinois one time in a seminar, I heard him say that if we'd have put as much effort into open-pollinated corn as hybrid corn, it had made as much progress. Was he just being provocative, or what do you believe about that?
What did your state say?
He said if we had put as much effort into open-pollinated varieties as hybrid-pollinated, or hybrid corn, we could have made just as much progress as open-pollinated.
Well, I doubt it, but myself, because each individual plant in an open pollen variety is a hybrid. 2 gametes made it so it is a hybrid. Now, whether we can get a collection of genotypes or individual crosses to be as good as one specific, I don't know. It seems to me like that would be nearly impossible because, like in my reciprocal recurrent selection, where I have 2 populations, and I was just looking at data the other night, and it's improved, significantly improved, but it isn't up to snuff with my best commercial checks. And heterosis improved from 8% in the original CO by CO to 48% between the C17 and C17. But the cross between the 17 and 17 didn't equal commercial checks. Now, they'll be similar to the old checks I had in 1963, those old hybrid, but I mean the current commercial hybrid check, so I think it'd be a tough tough row to hold, to get a whole collection of crosses to equal one specific cross. Now, that's not to say that that collection of crosses in certain situations is not better than that one specific cross. But even like cimet in the tropical and the lesser developed areas, it's in the hybrids now too. They discontinued or put less emphasis on their populations than they did, say, before 1985 or sometime. When Ron Cantrell went there, they switched over to hybrids also. And I don't know, there's a connotation, hybrid, you know. Like my mother's, you know, she had hybrid irises, or she had hybrid tomatoes. Well, they were hybrid tomatoes, but not because of yield, but for all the diseases they had, and they had crossed several, or a parent that had each of them different resistance to diseases to get hybrid tomatoes. But it was because of disease pressures. I'm not denying he's wrong, but I doubt it.
All right, looks like we got one more. We'll take the last question, and then we'll...
Okay, thank you again for the talk and for hosting this symposium. Do you have any advice for the aspiring breeders in the room?
Stick with it. Breeding is patience, patience, and patience, and you always have more failures than successes, but don't get disheartened and stick with it. You're always hopeful. Even at my time, you know, geez, I got a few lines out there. Maybe something will happen, you know. So we're always looking for that silver bullet. And it's kind of like you go down to the store and buy a ticket to the lottery. You know, get rich quick, you know, rather than work 40 years and buy something where you want, well, I get a lottery and win it in one day. So it's a very, to me anyway, dumb me, because I don't know molecular biology, it's a very satisfying career, and I enjoyed it, and you're outdoors and indoors, and you see nature, you know, operating on what you're doing, and you're selecting materials, you know, and you're always got some goal or a vision, or your boss does, of what you need to do to, you know, get a superior product. And it's a very competitive world out there, and so, you know, it's patience and study and work hard. And I don't know what other suggestions. A guy would like to be an expert in a lot of things, but you go to school forever before you get there, because I wished I knew chemistry better, I knew I knew this better, and I wished I knew that better. And so I guess you got to make linkages or connections with other people for those weaknesses in your portfolio of talents that you have. But patience and patience.
Thank you.
All right, well, let's give Dr. Hallauer one more round of applause.
Thank you.